Hello, everyone. Welcome to this presentation on Develop and Sharpen the Expertise of Radar Specialists. This morning, we will have a presenter. He's with me. His name is Gonzalo Mora. Good morning, Gonzalo.
Good morning, Francois Xavier. How are you?
Doing good, doing good. We have many attendees this morning. It's good to see.
Perfect. So let's get started. Right away to our topic.
Yes, sir.
Okay, so today in our agenda, we're going to talk about who we are, how we design our learning solutions, then what is a radar, then the available learning solutions that we have. We're going to make actually 2 demos, not only one, and then we're going to have some questions. As you remember, Francois Xavier is here with me. He's going to be handling several tasks like a cameraman, and he's going to be handling as well the questions and the chat. So please, if you have any question, just type it in the question box or in the chat box, and Francois is going to answer them directly, or I'm going to make some pauses and he's going to send those questions to me.
Well, I see that the questions box is working. We have greetings from Croatia already. So don't hesitate. Write anything that you may want to know about the system and about us.
Thanks, Croatia. So a little bit of the history of Festo Didactic. In 1925, Mr. Stoll started his company as a company that they were building machinery to work with wood for carpentry. In 1955, they changed of technology and they start using all the pneumatics, and we still do it now. In 1965, all the technology was evolving very fast, so they found out that it was a good idea to have training systems for the new technology so we can have good technicians and good professionals. In 2014, Festo Didactic purchases the American-Canadian LabVault, and then in 2020, we are a very big company dedicated to make didactic products. And right now, we are broadcasting from Quebec City in Canada, and we are very happy to be with you this morning or this afternoon if you are watching us from Europe. So part of the things that we do here is factory automation, process automation, fluid power. We do environmental and renewable energy, building systems technology, electronics, electric power technology, everything about industrial trades, telecommunications and radar technology, that is what we're going to talk a little bit today, and HVAC and refrigeration. Here we have a small picture of the building from which one we are broadcasting today. And the 3 guys in the right of the picture is from right to left. We have Mr. Christian Remillard. Then in the middle, the tallest one and the largest one that we have is Francois Xavier, that is today with us as the cameraman. And myself, the little guy in the left. So welcome again, and let's get started. How we designed our learning solutions. So designing a didactic product is not very easy. So we have to merge several things. We have to merge industry specialists, teachers that are going to teach and they're going to educate the new professionals. And then we have the Festo experts. So we join these 3 groups of people and we establish learning objectives. What should be taught, what the students need to learn so they can become competitive professionals, and how we're going to do this. Then we're going to establish a group of lab exercises that are going to allow us to explain to students what we need to teach and make the students grow in knowledge. After the lab exercises and the learning objectives are in place, we're going to make the equipment specifications. Okay, what hardware is going to allow me to explain all this theory? Once the equipment specifications are in place, we're going to get on to the learning systems strategy. So how we're going to join the theory and the practice. Once that is done, we're going to build the hardware. And after the hardware is done, then the technical writer that was involved in the project from the beginning will start writing the manuals that are going to accompany the systems that you're going to have. So all the exercises that we provide in our manuals are done with the real equipment. So you can be sure that when you do one of our exercises, the exercise is going to work. You can repeat it as many times as you want, and the results are going to be very similar. So before starting with radar, Francois, do you have any questions up to now?
No, I think now everything we should be ready to go.
Perfect. So let's start playing with this. So what is the radar? So it stands for radio detection and ranging. So here we have a small image of what our radar looks like. So we have this big square that is the target table. We have two piles of modules behind the student that is in front of the computer. And then we have here the antenna pedestal with the rotating antenna. That this one has a looking just like the ones that we see in airports, for example. So basically this will be how the system will look like when it's installed in a classroom. So where do we use radars? We're going to use radars, for example, for weather. We have stationary radars that are just taking a look to the clouds, wind, the ocean. There are some other radars that are finding what the weather looks like in front of an airplane. Also is going to detect other airplanes. And of course, air traffic control. This will be the part of the applications that we have that are closer to the civilians. Now we're going to take a look to another radar that is very close to the civilian, but we don't want to get it as close as possible. We try to avoid it. And you're going to see right away what I'm talking about. There are some countries that are really strict in speed tickets. So they have their radars in the police cars, and they are always detecting other cars to see who are going too fast, which ones are going too fast, and then they're going to be very happy to give you tickets. So this is the only radar you have to try to avoid. Then we have other applications of radar, like the defense radar, or we have everything that is related with pictures and images made out of radars. For example, the inverse synthetic aperture radar, the ISAR or the SAR. So here we have a kind of a explanation between a military radar, and right next to it, we see the Festo version of the radar. So all the radars that I am talking right now, we're going to be able to build them in minutes within the classroom and make exercises that normally we will not be able to do it. It will be very costly to grab, for example, one helicopter and tell the helicopter, okay, place yourself in this position in the sky, move to the right, move to the left, just to train the students in the radar. So that kind of testing and that kind of situations, we're going to do them in the classroom with the radar we provide in Festo. Perfect, so let's move on and let's take a look to which one are the available learning solutions that we have. In the radar, we're going to be able to configure our system in several ways. We're going to start we're going to start configuring the system that we have here in many ways, and we're going to use one of these modules, that is the RTM, that we're going to talk about it a little bit later, that this is the one of the key points of the radar among several that we're going to see. We have a lot of patents that we have made about this system. This system is unique in the planet. So this is something like a jewel for us. It's something really, really special. With this system, we're going to be able to reconfigure the system in several ways. We're going to make, for example, an analog pulse radar, or we can go to a digital pulse radar that will be the radars that we use in airports, in which ones all the airplanes that are flying around, they have their own flight number, name, company, and we find them which path they are coming in, their speed, and we make them approach to the airport. Then we can go to the tracking radar. For example, right now it's kind of in fashion, the movie Top Gun. So remember the scene that we have one plane chasing another one, and there's this the small circle with a cross that is being placed on top of the airplane that they want to shoot. And we see in the screen locked. So what happened in that scene is that the radar of the airplane that is chasing the other one locked on the other airplane. So we're going to recreate that in our radar. And we're going to explain how this technology works. How can a radar get locked into a target? All this is going to be explained in the tracking radar. Then we're going to pass to the phased array antenna radar. So after we have a good knowledge about the radars, we're going to change the antenna to the phased array antenna. So now we're going to have an electronic antenna that does not has any mechanical moving parts, so does not wear out. Has a lot of advantages. It is going to be faster and will not get damaged very easily. Then we're going to go to the phase-coded pulse compression radar. Pulse compression is going to allow us to have very small pulses and have a better resolution. Then we can go to the frequency modulated pulse compression radar. Then we can make tests about the radar cross section. So in this one, we're going to take, for example, airplanes. We have model of different kinds of airplanes, military airplanes and civilian airplanes, and different targets. And we're going to take the radar cross section. So we're going to find out how they look like to the radar. After that, we're going to go to the pictures and the images that we can take with our radar. So we're going to make the inverse synthetic aperture radar and the synthetic aperture radar. So we have 9 different kinds of radars that we can build up with the FESTA radar we're providing here today in this training, well, this webinar. Perfect. So now the next question. Okay, we're talking about a radar, we're talking about microwaves. Is it safe to have it in the classroom? Yes, the power levels we are going to use in our system are very, very low, and they're way below the standards that are accepted. So if we see here, we have the frequency range, we have from 8 to 10 gigahertz, and the output power at the horn in continuous wave mode, that is very few exercises that we use it in continuous wave. For example, when we are recreating the police radar, the gun that gives you the speeding tickets, we have 0.02 microwatts per square centimeter. So this is very low if we compare it to the standards. So we see that the black line, I don't know if I can use my mouse. Yeah, I can use my mouse. This line will be the most strict standard that we have, and we are 10 times lower than that in continuous wave. And in pulse radar, that's most of the exercises. I would say 95% of the exercises we're going to do it in pulse mode. We are like double of that in energy. So we'll be really, really small. We'll be not double, half, sorry about it. Now, all this technology is not very easy to teach normally. So we have developed for each one of these 9 radars we talked, the manuals that are going to accompany each one of the radars. All the manuals, they have all the theory already developed and a guided exercise step by step. So last night, I read my little pile of manuals just for you. So here we have part of the manuals that we have with the radar. We have a lot of knowledge in those manuals. So you can be sure that the teachers that are going to use the system, they're not going to be struggled with something complicated. We know that technology, we are talking about a high level, but everything in the manual is very clear and step by step. So if you just follow the exercises in the manual, you're going to go through a very good explanation of the theory in very simple terms, in very easy words. We avoid the complicated math. We just stick to the basic algebra that we need to make the real calculations and the real things. And we explain in our manuals everything about the microwaves and telecommunications that are involved in our radar. So our system, we're going to make it work in a couple of minutes, is a system that is real. So we're going to use the computer, and we're going to use the power of the computer to make this system become a didactic product. Between realism and didactic products, they are not the same thing. So we try to approach a didactic product to make it as real as possible. And in this case, we succeed. So when I'm going to start using the radar, you're going to see this is not a simulation, it's a real radar. We're going to detect the real targets in real time. And you're going to see that my target table is not connected in any way to my radar. So the detection is a real detection. It is going to be very easy to use because we're going to use the PC to make several tasks. So the students are going to be focused in building up the radar, making the connections, all the communications, and then using the radar. So all the elements that we have in the real radar, we have them in ours, but we have on top of this one layer that we can manipulate several elements that normally you will not be able to manipulate in a real radar. So this is how we have enhanced the didactic value of our radar. We can use our radar with all the virtual instrumentation that is provided within the system, or with just standard oscilloscopes and standard instrumentation. All the signals that we're going to find in our radar are real signals. So we can connect this to a real system and it will keep on working, of course, with the power it has. But we can share the signals and we can make a lot of different scenarios using ours and using other equipment. All the signals that we have are just real. In the software, we're going to have the ability for the instructor to introduce faults. So the students are going to be able to learn troubleshooting in the radar. Why the signal is not working, where I have a problem. Is it a physical problem? Is it an electronic problem? Is it a software problem? Or I have an electronic problem, for example, in more in the military area. If you have an electronic attack, for example, a hacker that is trying to damage your radar somehow. So here we're going to take a look to one of the exercises, just very quick to take a look how the manuals they look like. In the handout section, I have placed the datasheet of our radar and this PowerPoint presentation for you. Be sure to download them before the webinar finishes. So here we have the exercise objective. Then we have the discussion that we're going to go through. Then we explain the formulas. We're going to explain each one of the variables, and always we're going to place an example. For example, here we find out that with the values we have, a target is located 3 kilometers away from our radar. Then the next part in the exercise, we're going to find about the pulse length. So this is going to be related with the resolution of the radar. So the radar is able to detect objects at a certain distance, and how able is the radar to detect two objects that are very close. In this case, this radar is able to detect objects that are 300 meters apart. If it's an airport radar, 300 meters is more than enough. If you see two planes separated 300 meters, you're in the limit of having basically no planes. They already crashed. So this will be a very good resolution, or good enough. Then we're going to explain what kind of radars are coherent, non-coherent, super homodyne, homodyne. Ours, in this case, in the exercise we're explaining, is a coherent and homodyne receiver. So we're going to explain to the students, okay, we have the antenna, we have the pulse generator, and all the other elements that we have in the radar, how to connect them, how the signal is going to be created and be sent to the antenna. Then the echoes that are bouncing back from our targets are going to be captured by my antenna and sent to the receiver for further processing. So all these steps are going to be explained in detail. So how targets are detected? Here I have my antenna, and I have my pulse that right now is represented by that arrow, and I have two targets. So my arrow is going to go and is going to bounce back in my first target, but will not bounce back completely. It will go through the target and keep on going, and we have one part of it that bounces back. Then the same arrow goes through the first target, hits the second one, and bounces back again. And then we have two echoes coming back, that they have one separation. So now we're going to find out that with one pulse, we found two targets, but they have to have a certain position and a certain distance between them. Because if my pulse is too long, the same process is going to happen. I will hit the first target, bounce back my first echo, keep on going, hit my second target, bounce back, but my pulse was so long that the second target that is bouncing back, its echo, is going to join the first one. And now we're going to have a very long echo coming back. So for the radar, instead of having, let's say, two airplanes, we have one, but a very large one. So here we're going to explain to students all these little details this way. Very easy, very clear, so they have a very firm knowledge. So we're approaching to our first demo. So I'm going to explain a little bit what we're going to see in the screen. So we have here two targets, and underneath we have the oscilloscope. So that's how the targets are going to be seen in the oscilloscope when we find two targets. If we're in the limit of resolution because our pulse is too big, we're going to be in the middle condition. And at the right, the targets are not resolved. So we see just a very large target. So the best, of course, is the first condition, having our targets resolved. So right now I'm going to switch to my radar program. And I'm going to choose the analog pulsed radar. And it says connecting to the reconfigurable training module, the RTM. So Francois is giving me right now a picture in picture. So here we have our modules. Can make it larger for now. Thanks, Francois. So here we have the training module. The training module is going to receive the order from the computer and is going to reconfigure itself to be able to handle the signals from different kinds of radars. We have these three cards here that basically they look like this. So they have special functions on them. We have several cards because the RTM is used in the radar, in telephony, in analog telecoms and digital telecoms. So you have a very powerful unit here that just switching these cards, we're going to be able to reconfigure the system. So in this first half of the tower, we're going to have the radar transmitter. Here we're going to build up the signal that we're going to send. So we have a radio frequency oscillator, we have a pulse generator. Here we're going to mix them and send the signal to the antenna that, Francois, not that one. Yep, this antenna here. Okay, so comes to the antenna. In the antenna, we have a circulator. So all the signals coming in are forced to go to the antenna, get out of the antenna, come back to the antenna, and then we get the other cable, comes back, enters here to my radar receiver. Here we're going to start making the processing of the signal. Then we have the sampler, in which one we're going to be able to start making physical corrections to the signal, like the gain, the region. And then we have my two channels here coming to the RTM. Oops, one of the channels was not connected. Okay. Then from the RTM, we're going to make some processing here that I'm going to talk about a little bit later. And then here we have the display processor. Then we have the second module here will be the radar antenna controller and the synchronizer. So we have to fit the speed of the antenna and the signal that we're sending. So we're going to be sure that in each turn of antenna, we're sending the same amount of pulses as the antenna is turning. The other element that I'm going to show you here is this one. This is a remote control that handles the table. This one has a USB cable that the only thing it's doing is powering this unit. We try to avoid the batteries because sometimes, especially the rechargeable batteries, is a little bit of a pain when you have to make the export and borders and regulations. So with a USB powered unit, it's easy. So this unit, I don't know if you can make a little close up, Francois. Perfect. So here we have position of the target, speed, trajectory. In trajectory, we can make a circle, we can make a square, an infinite like a symbol, a line. We can make external control of the target table, or we can use it for synthetic aperture radar. In this case, I'm going to use it just in speed. I'm going to press it for enter, and I have there the actual position of my antenna and the speed. So if I move my antenna, you can see right away that my numbers move. So I can find out exactly where my target is positioned, and I can make it move at the speed I want. So this will be how it works, my target table. So now I'm going to switch back to my computer, and let's take a look of what we have. Here we have in the analog pulse radar, what are the connections that we're going to do? Then we have in the mobile target indicator processor, what manipulations we're going to do to our signal. And here we're going to start using our oscilloscope. So right now I'm going to use my oscilloscope, one channel there, another channel here. I'm going to sync it here. And I'm going to get my oscilloscope. Perfect. So I'm going to make some adjustments here. While I make the adjustments, Francois, do we have questions?
We're halfway through the presentation now, and I don't have pending questions for you, Gonzalo. But thanks for asking.
Okay, so can we get a picture in picture? So right now I'm going to press this button and start transmitting. I'm going to click the refresh, and I'm going to put my antenna to rotate. I need to change a little bit my time base there. And I am going to stop my antenna right in front of my target. So right now I'm going to cheat a little bit. Okay. So what you see in the screen is the target. So I'm going to move it by hand to make it very slow. And we can see like a butterfly. So this is how it looks when we have a moving target. I'm approaching to the end of the table. And now I'm coming back. So right now I'm going to change my target so we can take a look to the resolution. Okay. Perfect. So here I changed my target. I have my blip, and I'm going to put a second one. Here I have a transparent target, and I'm going to put it here. I'm going to make my time base a little bit larger. Okay, so right now my target is in the middle of the table. I would like my target to be in the middle of my oscilloscope. So I'm going to change the origin there. Yes, so this is my moving target, and this one is my fixed target. I'm going to move it a little bit. Aha. So I'm going to start approaching them. Let me put this one in a nicer position for you. There. I'm going to start approaching my moving target to the one that is static. There. So now we have two targets that are resolved, but I can change my pulse length. Okay. So that's my minimum pulse. I see that I have two targets resolved. I'm just going to change the pulse length very little by little. And now I have a very large target. So as you can see, if I grab my tape measure, this is one of the exercises that we're going to do with the students. Right now, I just did it in a very fast way. But if I measure the distance between my two targets, even though I did it really fast, is 25 centimeters. Oh, in this camera, sorry. So it is 25 centimeters. So this is something that always amazes me. Having a didactic system that is able to detect two objects just 25 centimeters apart at the speed of light, because this is what's happening here. Everything is moving at speed of light. I find it always amazing. I've been using the system for like 10 years, and it's always something very, very impressive for me. Okay, any questions?
Hello, Gonzalo. So far, I don't see any new questions. Just a reminder for the audience, you can go to the questions box, and then please don't be shy. We're there to answer any of the questions that you may have at the moment. Gonzalo, the demo that you did was it from the first manual?
Was from the first manual. One of the exercises of the first manuals. Yeah, this will be the maybe exercise number 2 or 3, in which when we start learning, okay, this is how an echo bounces back to the radar, and this is how we see it in the oscilloscope. Now I'm going to explain a little bit of how we're going to make further analysis with these echoes that we saw in the oscilloscope. And I remember you that I am just making 2 exercises of, I think is, yeah, this is the manual. In this manual, we have a for like 16 exercises, and it's like a telephone guide, and it's only one of the manuals. Yep, have a question.
I do have a question now. Yeah, what's the minimum system requirement for the connected PC?
Oh, with just a standard PC right now, I'm using my computer. It's just standard laptop with Windows 10. We don't need anything really fancy or really powerful. It's just a same computer that you'll have in your house.
Another question here. Do we have the manual available in Festo LX at the moment?
I have not used Infesto ALX, but since all our manuals are already in electronic mode, I imagine there will be very soon Infesto ALX, or maybe they are already in Festo LX. I have to check about this. Yep.
Mm-hmm. At the minimum, they will be available as a PDF. I'm
At the
thinking,
minimum,
but
PDF, and we'll have it in, of course, in English. We have them in Spanish and in French.
okay. And one more question for now. What's the emission power range?
The emission power range was, we said, well, in the beginning was 0.02 microwatts per square centimeter, I think.
Yeah, okay.
Yep.
Well, thank you. We'll have
Perfect.
more questions at the end. Thanks for asking.
Okay. So just to show that the system, can you give me a big picture? Yeah. Just to show how safe the system is. I would not do this. Right now, remember, I am in transmission. I would not do this in the real antenna. It's impossible. I've seen some students, because students are so curious, they're going to take a look here in the horn to see, oh, what's happening? They try to see if they can see something. Of course, they're not going to see anything here, but see, I'm putting my hand here. In the next part of the exercise, what I'm going to do is I'm going to put my hand here. You're going to see that I just kill all the signal, but it's safe. Don't worry about it. I've been working with the system and everything works fine.
Of course, we want students to use the right technique and
Yeah,
do safe things, but that's the time to learn.
yep. So we're going to explain that they don't have to do that because they may try to do it in the real antenna. It's not safe. But yes, the system is really safe if the students make that kind of mistakes. And we know they are curious. Okay, so now let's go back to our PowerPoint presentation. Okay, live demo, we did that. So we did talk about the RTM. So in the RTM, we're going to change the cards that I told you. Those cards, they have, we see in the upper part, we have external hooks, so we can grab oscilloscope plugs there, and we can check the signals in all the elements that we have. So we can check how the signal is going to be manipulated in all the steps. Then we get the mobile target indicator. In the mobile target indicator, we're going to find all the filters that we have in the system so we can manipulate the signal. Basically, each one of the boxes that we see in the screen will be one chapter of the book. So we're going to explain how this one works, why it works in a certain way, and then we're going to make one exercise so we can use it. We can get really in detail. All the blue dots that we see there are testing points. So we can put the oscilloscope probes in all those blue positions. All the calibrations and configurations are done directly in the screen. So we can recreate several scenarios, just changing the configuration in the screen, and we're going to have new behaviors in the radar. Everything that we built within the radar is very easy to set up. Building up the antennas, making up the new configurations, everything has BNC cables, for example, and we have these special clips for the antennas. So you're not going to be wasting time building the system than using it. In case of repair, everything is modular. So if one of the cards gets damaged, we can replace the single card, one part of the module, the full module, because we produce everything here. So we can make all the parts that you may need. In some of the applications, we need airplanes. So we're going to provide with airplane models, civilian and military, that they have been coated with a special paint that is reflective to radar. And they have these pink supports that's made out of a material that is invisible for the radar. So when we put it in the system we provide, these airplanes for the radar, they look as if they were flying. So we can place the airplane in a specific position, basically in the air for the radar, and manipulate it to take a look how it looks when it's coming towards us, when it's flying away, when it's moving in front of us. So how the radar will react to that. We can create different scenarios in the radar. This is a picture of the radar that I took some days ago in the position it is now. So when we're going to use it right now in the demo, we're going to see what we're seeing, and I'm going to explain you what you're seeing right now in the screen. We use state-of-the-art DSPs so we can have very fast response in our signals. So just to remember, this system, it is not a simulator, it's totally real. All the signals entering the system can be monitored and measured with the virtual instruments, or from here, we can use just the standard oscilloscopes and standard instruments. So if you can measure any external signal, if you plug it here, and if it's within the ranges, we'll just measure it with our system. So everything is real, everything is works, but is very safe. So the system is designed for students, is designed for teaching. So you can do all the experimentation that you want. We can make within the same system, for example, a Doppler radar, a frequency modulated continuous wave radar, like an altimeter for the planes, and the pulse radar with an A scope. So those exercises, actually, we're going to do them without the RTM and using just a basic oscilloscope. So we're going to be using both words, the real world and the one that we have in the computer with the instruments that we provide. Here we have a match of the mobile target indicator or the mobile target detector, the MTD. So those little dots, the pink, blue, and green that we see around the screen, those may be airplanes. So we're going to explain how we're going to process the signal and then how we're going to detect them and then name them. After that, we're going to follow the path they are flying in. So this is how the radar of air control works. And then we go to the images. Here we have how the airplane, this stealth airplane that is not very easy to find by the radars, looks like when we make a radar image SAR of it, an ISAR of it. So we're going to reconfigure our radar and we're going to start taking a look of how the targets may be captured as an image using the radar. So since our system is PC based, we can change the language of the system very easily. So directly in the software, we just change the language and all the interfaces are just in the new language, and we can use it for several different languages in different countries. So our computer allows us to have several windows with a lot of information. So we can manipulate the signal and see the consequences of this manipulation directly in the screen. Or we can configure the radar, for example, for speed. This will be a fast Fourier transform, and we see here 3 different scenarios with 3 different fast Fourier transforms for the same target. So the amount of knowledge that we can have with the system is really, really deep and is a very good quality. And this will be the reflection pattern of a target. So how the target is going to reflect the echoes, that is when it is surrounded by radars or when it is turning around. So how that radar is going to look at in all the sides. Here we have an image of the phased array antenna, but I'm going to show you some of the elements here in real. So started from here, we have our phased array antenna. We have the antenna. In the back, we have all the controls, and we have this small door here that if I open it, we can see how the antenna works inside, and we have a lot of test points. So we can see how the antenna is going to be driven. Then here we have some of the elements, different kinds of targets. For example, this will be the cylinder. This will be a plane coming towards the radar or a plane that is moving sideways. We're going to provide with special antennas like this one, that this is for the pulse compressor. Different kinds of targets. And this one. This one is our jamming pot. One of the books that we have is how a radar can work in an active target environment. And what would be the measures in the countermeasures in the case you have an electronic conflict. So we're going to jam a radar with the jamming pot, and the students that are using the radar are going to find out what are the real measures, the good measures for different scenarios that we're going to create in this jammer. So we're going to try to attack the radar, the group A, and the group B is going to make the countermeasure to keep the radar working. So of course, this is a more military application, but yes, we cover also the jamming pot. Good. So right now, we are finishing our presentation, and let's go to the demo. Okay. So now I'm going to go back to my MTI, and I'm going to change my target here. And I'm going to put my antenna to turn. Okay. So here we have the radar antenna. I'm going to change it to color coded. And we see our PPI. So I'm going to move my origin. Yes. Too much. Okay, so what we are seeing here, all this line of targets are the stats in this wall. This one here is my stack of modules. this little target here is my computer, and this one is the moving target. So I'm just going to stop the target, and we're going to make a small exercise. I'm going to move it by hand, put it in any position, and I am going to measure. When I'm installing a radar in an airport, for example, I have my target, and I have a physical target that I'm going to place it somewhere that I know, and I put it in that condition in purpose. So I know target A is going to be 10 kilometers away from the airport, north 35 degrees east. And the distance in this case is going to be 160 centimeters. So what I'm going to do is I am going to turn on my bearing. Okay, so this target, its real position is in the cross. So what I'm going to do is I am going to move the origin of my radar electronically so I can match that. A little bit more. Let's weight the antenna. Too much. A little bit less. Okay. So now I matched what my radar is looking to the real distance of my target. That's exactly the same thing they are going to do in an airport to match the real position, calibrate the radar. Of course, they're going to do it with a lot more detail of what I did right now in several seconds. But basically, this will be the idea. So I'm going to take out these elements. And right now I'm going to change something in my radar. Something that we have a problem with the radars. So I'm going to put my target back to move. Okay, is clutter. The clutter will be everything that is annoying the radar. For example, rain, sea waves. So how I can put rain or sea waves within the radar? I'm going to put some rain right now. So I'm going to turn on, for example, rain. I am going to put a kind of a heavy rain right now, 80%. And we saw that we have rain right on top of the target right now. So all this that you're seeing here is exactly how rain looks like in a real radar. How we do this? Remember in the RTM that I told you that we grab the signals to the RTM here. In the first car, what we're going to do is we're going to inject an artificial signal and add it to the real signal to create the rain or sea clutter. For example, let's put some waves. Let's change this to 90 degrees. So let's put the waves somewhere else. So let's say I'm going to put my waves behind, so near the wall. So the waves are all this part here. waves affect the radars only when they are very close to the radar. So here we get a very quick view of what our radar is able to do. Hopefully you have a good idea right now of what are the capabilities of the radar. And Francois, do we have any questions before we finish?
Yeah, one last question. How many hours of training does that represent?
Okay, how many hours of training does that represent? Each exercise can be done in around 2 hours. So depending on the deepness of the radarist you want to build on, you can have with one book, with the book number one, that is the one that I'm using now, you may have like around 50 hours of training. All the manuals together, I would say like 200, 250 hours of training in radar technology. So the students are going to be very, very good based in all these kind of technologies. Any other question?
Yeah, one more. There's a radar company called Thales. They
Yes,
do
I know
training.
those guys. I've worked with Thales. Yep. And Thales uses our radar to train their people because Thales is a very large provider of radars for airports. They make huge projects, but they use our system to train their employees and to train their customers when they have for example, a new airport. I remember in Bolivia, they made a full airport with all the telecommunications and everything. And in the training center they did for the airport, they had our radar, and I went there to make the training. Thanks, Francois. Very good question.
Yeah, that's it for now. I think we can. Oh, there was one more. Do they sell our equipment to end users, or is it us? But that's a question more for the sales people, maybe.
Yeah,
So I
that
would.
question will be more for the salespeople. Yes, we have been selling this system for a lot of years. I would say like 15, something like, and or more. So please just contact your Festo local company or our Festo dealer, and they will be able to provide you all the information about the process to purchase these kind of systems. For me, it has been a pleasure to be with you this morning or this afternoon, depending if you're in Europe. Thanks so much, and keep up with the newsletter. We're going to have another group of webinars coming in December. Thanks so much. To the next time.